Good evening, everyone. Welcome back to the seminar series of IvS. Today we have Princy, whose last name I don't even dare to pronounce. Sorry, Princy, for that. Princy comes originally from Madagascar, I believe. He did his bachelor and master studies, but apparently was not really satisfied with that and decided to do another master in astronomy in Manchester successfully. And presently, he is a joint PhD between KU Leuven and Radboud University in the Netherlands. And today, he's going to be talking about his PhD thesis topic, which is the characterization of population of hot but sub-luminous stars. And Prince is using multicolor photometry as the data set and machine learning tools as the methodology. So the floor is yours, Prince.
Thank you for the great introduction. So my name is Princy. Today I'm going to talk about my project as introduced on hot subluminous stars using multicolor photometry and machine learning. My talk is divided in 4 main parts. First, I will give a quick introduction to hot subluminous stars. Then I will talk about my project on frequency analysis of multicolor photometry. Then I will discuss my project on the variability of hot subluminous stars using machine learning techniques. Then I will end up my talk with a summary and future work. But now let's look at the first part of this talk. So hot subluminous stars are they represent the population of blue and compact evolved objects. As you can see in this color magnitude diagram, they are located at the extreme horizontal branch between the main sequence and the white dwarf sequence. They are divided into 2 main spectral classifications. First is hot sub of B, and the second is hot sub of O stars. Observations confirm that HTP stars are the most common, so my talk will be focusing particularly on HTP stars. These are hot and compact objects as suggested by the effective temperature and the surface gravity. But why are HTP interesting? First, they represent a different evolutionary path compared to normal brain stars. This is because they have very thin hydrogen envelope, and this suggests that these are the stripped cores of low-mass red giants. Second, the majority of hot subluminous stars are found in binary systems with cool and low-mass main sequence companions, main sequence stars companions, and white dwarf companions. And these are also important populations to study binary interaction processes such as mass transfer, common envelope evolution, and mergers. Another aspect of HTPs is that a subgroup of them also pulsates. So these are ideal populations to study stellar interiors and with asteroseismology. Lastly, a group of some of these HTPs also represent potential gravitational wave sources and supernovae progenitors. These are essentials. These are particularly true for the short period hot sublows with white dwarf binaries, and 3 of them are known so far to be likely gravitational wave source systems to be detectable by future gravitational wave surveys. Now let's look at the ongoing research on hot sublows. So the main focus on the research on hot sublows is mainly on formation and evolution of this object because they are not fully understood yet. So studies focus mostly on understanding the formation and evolution, and examples of this research is, for example, pulsation and asteroseismology to understand the interior of these stars, Some research focus on theoretical modeling to model the formation and evolution. And this leads me to the goal of my research. So the main goal is to study the variability, to understand the process behind the formation and evolution. But there are some challenges in this project. The main one is how can we deal with sparse and irregularly sampled time series data. And the methods I used in this project is mainly focusing on frequency analysis and time series analysis. Now let's move on to the first part of my project. So this project is about the frequency analysis of sparsely sampled light curves data. And the aim of this is to effectively estimate the dominant frequency in the regularly sampled light curve data, mainly from the ground-based telescopes. But before we talk about these are some points that we need that characterize ground-based observation and what makes our light curve, our time series analysis quite challenging. So first point is that we have to deal with non-continuous observations. Second one is atmospheric noise, which introduce aliases in the low frequency domain. And these points leads us to low photometric precision for ground-based data compared to space photometry. And the approach we used to address this challenge is using this so-called hybrid frequency approach, which combined Lomsky-Ergol periodogram with the Lafleur-Kinman statistic. This is a subclass of the phase dispersion minimization, but it is designed to deal with scarce data. So as you can see on the plot, on two plots, we see an example of Lomsky-Ergol periodogram. Most of you know this, this approach. And the second plot is the Lafleur-Kinman statistic, and we can see the aliasing frequencies, like the noise in these periodograms. So in the hybrid periodogram, as you can see on the plot on the right, we can observe the improvements in the noise levels compared to the two individual methods. So yeah, this has proven effective in determining dominant frequencies, dominant frequency in sparsely sampled data. So our first application of these methods is on the mirror-lit observations. But before talking about this, let me give you a quick overview of the mirror-lit telescope. This is an optical telescope located in South Africa, and this is the prototype of the Black Gem telescope array observed in the southern sky with 6 filters. But if you are more interested in this telescope and its this survey, you can have a look at this paper, a recent paper by Groot et al., 2024. So to apply our methods, we have to select our hot sub of candidates. And to do that, we built this mirrored color magnitude diagrams using the G minus I color and the absolute Q magnitude on the left. This consists of about 600 candidates, as you can see in the blue circles. We select this based on color selection criteria, and the same object is represented on the right using the Gaia photometry. And this shows that we can achieve similar photometry with Gaia using the mirrored observations. So I'm going to give you some outlook of the results. First, you can see on the left an example of frequency analysis using the Lafleur-Kinman statistic. In the middle, the lump scale called periodogram, and on the right, we can see the resulting hybrid approach. And we can also observe the improvement in the noise level. These three light curves is typical for, these are typical for the mirror-lit light curves. Yeah, so this is just to show you how they look like. So to summarize this project, we have developed this frequency search tool to determine the dominant frequency in sparsely sampled time series data. And we also saw that the mirror-lit telescope is capable of determining this dominant frequency using such method. Now let's move on to the second part of the project, or the third part of this talk, where I use unsupervised machine learning to detect, to analyze the time series of odd subdwarfs and binaries. So this is just a quick reminder that in hot subdwarfs, the majority of them are in binary systems, and a subset of them are in exhibit pulsations. So this means that variability is an important tool for us to understand this object. This is because hot subdwarfs exhibit diverse types of variability, such as ellipsoidal variation, reflection effect, and for the binaries, while for pulsating hot subdwarfs, they can exhibit gravity modes or pressure modes, and some can be found in hybrid pulsator. So there are also challenges in selecting candidates, as we saw earlier, especially for hot subdwarfs, because many of them are contaminated from main sequence stars and CVs. And as you can see in this figure, the CVs in the right, left triangles are mixed with the other variable hot subdwarfs. So it's very hard to classify them just based on this diagram. Next is that in the literature, candidate selection is mainly based on color and proper motion selection criteria. So this could also include bias in the selection, because we might select other type of stars. And for the variability detection itself is quite challenging if we based our selection on simple statistical parameters or a couple of statistical parameters. And this plot is just an illustration on any kind of statistics if we try to classify non-variables and variables using such a technique. So for example, in the blue ones are the non-variables and the orange ones are the variables. So we can still see some overlap between these two data points. This is just an illustration, but this is true for different statistics we tried. So the aim of this project is to alleviate and to address these issues by using unsupervised machine learning techniques to detect and characterize the variability of these objects. But before we talk about this, let me give a quick overview, introductions to supervised machine learning for those who are not yet familiar with. So unsupervised machine learning deal with we don't have the labels when we train the models, as you can see on the right plot here. So the model tries to understand the structure inside of underlying or data, and the goal is to get something like clustering, as you can see in this plot, and we tries to label them. But for the supervised machine learning, we know the labels of the data. For example, we know this part of the data are blue or red, and most of the supervised machine learning tasks are focused on classification or prediction. So in our case, we use this unsupervised machine learning, and this consists of three main tasks. So the first is we first extract our data, and of course we use Kaya light curves here. And the next step is to extract features, which mainly consists of determining the frequency, dominant frequency, and extract statistical parameters. In this sense, with many statistical parameters, because we collect as many features as possible. So we have number of features more than 2 parameters, and with that we need a dimensionality reduction algorithm to visualize them in the 2D space and apply the clustering tasks. So in this project, we use the Tisney algorithm, which is a nonlinear dimensionality reduction technique to visualize this high dimensional features space in lower space. As mentioned earlier, the first step is to extract the data. So we start with this catalog of hot subgroups, which consists of 60,000 objects. And then we extracted the light curves. And in addition to some quality criteria, we obtained about 1,500 light curves, objects with Kaya light curves. So we based our analysis on these objects, and the next step is to extract the frequency, the periods and amplitudes using the hybrid approach we discussed earlier. Then we extract statistical parameters from the light curves. There are quite many, but one of them is, for example, we count the number of peaks above the 0.5 of the hybrid periodogram, as you can see in this plot. And the rest of the features are from the Kaya summary statistics, color, and also some parameters from the Kaya source database. And this results in 84 features in total. So now we have these features. We need to select which one are the most important and meaningful for our analysis. So we remove all of the highly correlated features, and we end up with 49 features. And using the Tisney, we got this plot here. You can see that there are about 3 main clusters. The orange data points consist of candidates that we manually visualize as base. So we place them in this diagram to see if our analysis makes sense. So so using these 49 features, we obtain these results, but we still want to improve these results by removing the least important features. So we ended up with 27 features, which results in this plot, as you can see here. Then we label them as cluster 0, cluster 1, and cluster 2. And the next step is to understand what type of objects are in each cluster. So to do that, we cross-match these objects with the literature, and Also, for those who have trace light curves, we extracted light curves to confirm the variabilities, and those that we could match from the literature, we consider them as new variables. And after this, we have these results in this plot, where we identified two main class of objects. In cluster 0, we found most of the hot subdwarf variables, such as HWFR systems, reflection systems, and ellipsoidal variables. And in cluster 1 consists of all of unclear variables. And cluster 2, from cluster 2, we identified cataclysmic variables from the literature. So this is a very interesting result, because we can now separate CVs from hot subdwarf variables. And when we looked at the amplitude distribution from this Disney components, we can see that the amplitude is quite contributing in separating these three clusters. And to see what kind of objects we can find in kind of light curves we can find in the each cluster. In cluster 0, the typical light curves look like this one on the left. Yeah, and the same for cluster 1 and cluster 2. And these are to show you some of the hot subdwarf variables we found in cluster 0. So on the left, we can see an example of reflection systems. So these are mainly hot subdwarf with cool main sequence companions. In the middle, we can see an example of eclipsing reflection systems. And on the right, an example of ellipsoidal variables we found from the from this cluster 0. And as you can notice, that we also overplot it with the test light curves. This is to get a robust classification, especially, for example, in this case where the Kaya missed this number of data points due to the sparsity of the sampling. So it is essential to have the test data to confirm this in such case. Next, we can see an example of high amplitude pulsating variables. And these two objects are found in cluster 0, and these are also potential blue large amplitude pulsators candidates. This pie chart is just to show you the number of new variables we found from this analysis, such as these are mainly reflection and HWFR systems from the Kaya and TESS data, and also in the Kaya light curves we found quite a lot of new HWFR systems. And for the CVs, these are we cross-match them with the literature, so we can confirm these 140 CVs, while the rest we consider them as candidate CVs. So to summarize this project, we have developed this technique for detecting and characterizing variable hot subdwarfs. And this is the first time we use such technique to separate hot subdwarfs from CVs. And this approach is also flexible and can be generalized to any light curves data. So our future work includes extending this to larger data sets. So Yeah, so as you can see in this plot, we select all of objects between the white dwarf and the main sequence, the right data points, and these are from the Kaya data. And on the right, it is just a temporary results we have so far, but we are still working on optimizing these models. But it already shows that we found hot subdwarfs in the green CVs. Most of the CVs are in the right data points here, and also the blue ones represent most of the clear variables. So if you are interested in this project, if you want to know more, please have a look at this paper. And that ends my presentation. Thank you.
Thanks, Princy, for an interesting talk. We have plenty of time for discussion. Feel free to bombard Princy with questions, including machine learning, Pablo.
Thanks, Princy. Actually, I want to start with a non-machine learning question. So in the first project, when you were computing this hybrid periodogram for, it was not clear for me, how do you apply that with in the case of a multi-band light curve?
In the case of what?
A multi-band, having multiple bands. You mentioned that your light curves have many bands, like 5 or 6. So how do you combine the periodogram of each band? How it's
yeah, you can use 3 bands or 1 band using this technique, but in this case, in this paper, we combine the 3 bands from Earth telescope using the U, Q, and I bands. So we normalize the light curves using RMS to have using the Q band. So first we normalize the U and I band using the RMS from the Q band when we combine the light curves data. So it's like
it's like
an umpire.
You convert it to a single time series then.
Yes, yeah.
Ah, I see.
Yeah.
They might have phase variations. No?
Sorry?
They might have phase variations. If you combine everything in one light curve, you ignore that they can have a phase difference.
We use we phase them first using the we phase them using the same epoch. So, like we take the minimum of the time series and subtract it for the overall the combined light curves. Yeah.
Okay, and the second question is on the project of machine learning one. So why did you try the clustering on the 2D and not in the 21 or 29, I think, feature space?
Can you? I don't understand what you mean.
Yes, so if I understand correctly, you compute a set of features, then you remove features that are highly correlated, and you end with a set of, I think it was 29. Yeah. And then you use the TSNE to compress to 2 dimensions.
Yes.
And after that, you perform clustering with the Gaussian mixture model, but you do the clustering on the 2D instead of the 29. Or not?
No, we use the 27 features to obtain these results.
Yes, but is the clustering applied on the 2D space or the 27?
No, on the 27.
Ah, yeah. Oh, perfect. Yeah, because TSNE is known to distort the distances. So, that was the question. Yes.
Okay, thanks.
Well, I have many questions, but let's first start with the periodogram. So it's very nice that you start to use Lafleur-Kinman, something I'll already started to use 25 years ago. So you use Laffer-Kinman and Lomskagel on the same data sets, and then you multiply this. How do you justify this multiplication? Except that it works, but
I think we didn't invite these methods actually, but these have been proven very very effective by this paper using this research from this research. So you mean why do we multiply or what?
Yeah, I mean those two statistics are correlated because they've been done on the same data set, and then you multiply them.
Yeah, that's a very interesting question. But the reason why, we just saw that, this works very well with multi-band and sparsely sampled data that these people use, and we just use the results. And we just applied this to this mirrored light curves data, but I'm not sure I can explain you right now on the top of my head how they came up with.
I'm doing the same. I was just wondering whether you had figured out a good mathematical justification to do it.
I think I've got some similar questions, but they didn't really explain this in the paper, actually, but I can have a look again and see if I'm,
you use 80 features or parameters in your analysis. Can you give us a little more description of what are those parameters that you're using? Because you only provided a very high-level description of the features that you use.
I don't have all of the 84 features, but I only have the 27 here. So these are an example, descriptions of the features. For example, the amplitude, the interquartile range of the light curves. What else? We also use, for example, the false alarm probabilities and so on.
Okay, that's interesting. It's in your paper.
Yes.
Okay, I'll have a look. And the last question, of course, is you're now able to classify zillions of stars, but what did you learn about hot subdwarf? Or what will you learn in the future when you will have time to analyze those zillion data that you've classified?
Yeah, so if we, because in this project, we plan to find many pulsating variables, and so far we only found 2 objects. In the future, if we extend this, and so the main goal of my project is to understand the pulsating hot subdwarfs and to use asteroseismology to understand the instability strips, because some subdwarfs pulsate and some don't. So we want to understand this, and having many objects, non-pulsating objects, is very useful to understand pulsating hot subdwarfs in general as a population study. So
All right, thank you.
Hi, thanks for the talk. I was wondering, you use fully unsupervised learning, right, in general?
Yes.
So never at any point do you actually use the labels of stars that you already know to be, for example, cataclysmic variables. And I was wondering why you made this choice maybe in the first place, and whether there's methods where you can actually use the labels to get maybe tighter constraints.
I'm sure. I'm not really sure if I understand the question, but you mean why we use the...
Yeah, sort of semi-supervised learning, in a sense. Whether that's a possibility you consider.
First, our first result is just without these orange data points. You know, it just the clusters, and it's important to understand if these are meaningful or not, because sometimes if you don't optimize these models very well, this sneak can give you just many clusters, and many of them don't make sense.
Yeah.
And then that's why, because this is the first step, and we want to make sure that this is really, these results really make sense. And so we, select, just have a quick look at light curves that we found. We have no thought that these are variables, and then we put them in the clusters results here. And that's how we have these orange data points. But if you, it's a kind of semi-supervised in that way, but we don't use these labels for, to get.
Yeah, so it's
clusters.
just for a quick check of the clusters pretty much at the end to see if they make sense. Maybe a second question I had was, you use this TS&E method and then this Gaussian mixture to define your clusters.
Yeah.
And I was wondering, is that a conscious choice? Like, did you have a look? Is it because of the properties of TS&E and Gaussian mixtures that you chose them, or did you consider other methods as well?
Yeah, I think we don't have to. For example, if you have these results, you can just say like, I want make a free selection of these objects because it's pretty clear. You can just select these as clusters 0, cluster 1, cluster 2. But the Gaussian mixtures, it doesn't have. You can also use k-means clustering. But with the Gaussian mixtures, you can get a probability of each of the data points to belong. For example, it outputs something like these data points have 70% probability to be in this cluster, and 20% in this one, and 10% in this cluster. So yeah. That's why we used it in the first place. But I think it doesn't really change your analysis if you also use k-means, for example, in this case. But
all right, thank you. Very cool results, by the way.
Thanks.
We still have time for questions.
Hi, Princy. Thanks for the talk. My question is related to the first project of yours with the sparsely sampled light curves. Maybe I missed it, but I didn't pretty much catch why. How do you actually deal with the sparseness of the data points? So the fact that they are so, does it also the second part of the question is, does it not affect your results depending on like the phase coverage of your data points, et cetera, et cetera? Like how sparsely can they be sampled? There should be some limitation on at what point can you not anymore find the dominant frequencies and do stuff.
Yeah, so we, you mean why do we have sparse light curves from the ground? Is that correct?
No, why I know, but how do you deal with the problem that they are about the gaps and the sparseness of this? Like, is there some kind of interpolation done? Like, how do you?
So first we have capped data because of observing schedules and so on, as you can see here. Like, so we take data, for example, today, and after 2 weeks, and then we have another observation. And how capped is it? I don't think I have the. I think I missed. I have an example of light curves somewhere, but I'm not sure for some reason it's not included here. But I plan to show you some example of the sparsely sampled light curves. But yeah, it is like. to give you an idea, we took only a number of observations above 40 data points. So yeah, that's how low it gets to for the space data. But there is research shows that we can also use 25 number of observations to be able to detect the variability in the light curves data. And for this, how do we deal with this? Is we use this the Lomscale periodogram. It's a kind of it's developed to deal with irregularly sampled data. So it's like an estimator of the Fourier transform. So yeah, because the Fourier transform deals with continuous data. So in the Lomscale call, it's an approximation of the Fourier transform. I don't have the mathematical formulation of the Lomscale call here, but it just how to say that? It just an estimation of the Fourier transform. Yeah, I'm not sure if I answer you correctly.
Yeah, it's okay. We can discuss further later.
Hey, Princey. I was wondering about the final project that you showed, where you took all the stars between the main sequence and the white dwarf sequence in the Gaia. Do you happen to know where the clusters that you found lie on the CMD? So do all of your variable hot subdwarfs are actually hot subdwarfs in that CMD?
So this one, for this one, we only limit ourselves to up to 1 kiloparsec to avoid reddenings and so on. So yeah, a subset of this of the previous ones are already included in this green, blue data points and the green ones. So yeah, most of them are, all of them are already in there.
Well, my question was actually whether all the green ones up there correspond to the clump that you can see in the CMD in the top left, or are they scattered over the CMD?
The green data points, I should have put the plot here, but they are localized in this area with some few outliers here. But yeah, I can show you the plot later.
Okay. Thank you.
Nico, oh my gosh, but after Alex.
Yeah, hey, Princey. I was just wondering, could you give a bit of an idea of eventually with BlackJam and everything else, once you've got the full data set, what sort of physical stellar properties you'll be able to get for these systems, particularly the CVs?
I'm not an expert in the CVs, but people have been trying to, when selecting hot subdwarfs, people have been trained to separate them with hot subdwarfs. Some people only have interest in hot subdwarfs, some only have interest in CVs. So this result is just to make it, to facilitate the detection of CVs and separate them from other classes without using spectroscopic data. But research for CVs, I don't have, I'm not really working on this kind of study. But
all right.
Yeah.
Thinking about your health, Andrew. Very nice talk, Princey. I was wondering, so these T as and E components, they're nonlinear combinations of the input parameters that you have. Is it now easy afterwards to also interpret them in terms of observables? Can you explain, or could you explain hypothetically what component 1 means? And if you then see a new star, can you say, I see that this has a very big component 1, or is that impossible to do?
Yeah, that's a good question. And actually, we fortunately you cannot do that for the Disney components, because it's kind of an abstract combination, non-linear combinations of all of the features. So you cannot say that this component corresponds to which, because it's the combination of all of the 27 features. So it's very much similar. You can also do that with the PCA, for example. But yeah.
Hi, Princy. Thanks for the talk. I was wondering why exactly in this plot, for example, you only interested in the SDB stars. Why do you include all the other stars here? You already can see from the top left corner that they're going to be there, right? Except maybe for a few that would be very redundant. But
yeah, but if you observe, for example, up to like 2 kiloparsec or higher, you might include many objects in this area, and it becomes very hard to separate them. But yeah, this is suggested by one of my collaborators to also see how flexible this method is to characterize other types of variables. So that's why we extend it to this part.
So you believe that all of those, they could also be binaries, basically, the whole lower left. Okay, so that's why you include them, basically.
Yeah.
Yeah. Okay. And maybe I have a second question, if it's okay.
Yeah.
In your clustering method on this right-hand panel here, you, for example, take all the hot subdwarfs that you were interested in. You can sort of like maybe from the if you just keep on the same slide 50, which you were on.
Okay.
The right-hand plots. So you have kind of 2 clusters there. I'm just wondering, is there any physics? If you would plot it back to the clump, could you actually say something about the physics of these stars?
Which one is it again?
So take the green dots in your diagram on the right. You already used a Gaussian mixture model, right? So you could basically just fine-tune the grids and maybe fine-tune clustering here. Would you? Is there any physics to be learned maybe from further clustering of these things? That's my question. Maybe.
You mean for the green ones?
Yeah.
Not yet. We are still working. This is just a recent result that we got, but we are still working on identifying all of these objects, cross-matching them, and but so far we know that most of these objects in these green ones are, when we cross-match them with pulsating hot subdwarfs catalog, we found that most of the pulsating ones are in these clusters. And now we plan to cross-match with CTF and test letters to find more pulsating ones.
Okay.
But so far, we don't know. You mean physical process behind the green ones?
Okay.
Yeah.
Are there any more questions? So, Princy, I'll have a couple of questions here. You're hunting for pulsating variables. Do you still use exactly the same set of 27 features, or do you believe they are also robust to look for pulsators, and why?
I missed the second question.
So you use 27 features to distinguish between the SDBO stars and all the rest, right? Now you're looking for pulsators among those SDB and SDOs. Do you still use exactly the same set of 27 features as before for this, or
in this feature?
Yeah.
I use the same 27 features to in this work here.
What's the reason to believe that these features are robust? Because it's a different.
That's yeah, that's a good question. Yeah, we want to see first how flexible these 27 features, but we are not limited to using only these features because, yeah, that's my next plan is also to start with some number of features and yeah, do the same process as the previous project, like select which one, because maybe the 27 might not describe this all of these objects in this area, because we only focused on this area of the CMDs for the first project. Yeah, so the next step is to explore the features, and I also want, because in these previous ones, we only found all of the hot sub variables in these clusters, in this one cluster. And yeah, my next plan is also, we want to separate each of these variables so that we can, for example, have a cluster only for ellipsoidal variables, one cluster for reflection effect, and one cluster for HW first systems, for example. So yeah, trying to find a way to do that.
Okay, and so question on combining light curve from different bands, to pick up maybe on Joris's comment here. I think that's okay for this purpose when you care about things like reflection or ellipsoidal variability or eclipses, because I think you do not really suffer a lot from like phase shift present. But when you hunt for pulsators, that becomes a very strong argument, I think, against doing that, because the pulsation phase is going to be different depending on like what passband you look at. And if you combine all the different passbands together, you might be just smearing out some of the signal that you're actually looking for.
Yeah, that's a good point. And yeah, so I forgot to mention it, but we only applied it in the first project, but in this one we only use one band. We computed the hybrid approach for the G band, the PP band, and the RP band in the Gaia light curves. So we don't combine
anything here. Okay.
Yeah.
Any more questions? Last chance to ask a question. While people are thinking, is Manchester red or blue?
Blue.
All right, no more questions. Let's thank Prince again.
Thank you.
Thanks for coming. See you next Thursday.